Hello, here's our video for Chapter 7, Section 3, Reaction Stoichiometry. As always, you'll see the learning objectives listed here at the top. Please pause the video for a moment and copy down those learning objectives in your notes. As we get into reaction stoichiometry, the common analogy that is used is that of baking. So I have some information here. I've provided for you a cake recipe and ingredients that you have on hand. So say this afternoon you decided you felt like baking a cake, you went into your kitchen, checked your cupboards and fridge for the ingredients that you needed, and so those are the ingredients you have on hand. As you can see here, the recipe calls for flour, sugar, eggs, milk, and baking powder to make one cake, and here are the ingredients listed that you have. So the question becomes, how many cakes can you bake today without having to go to the store? If you said one, then you're correct. And the reason being is you are limited by the amount of cakes that you can make based on the amount of eggs that you have on hand in your kitchen. You have excess ingredients of flour, sugar, milk, and baking powder, plenty to make multiple cakes, but because you only have 2 eggs, which is exactly what the recipe calls for, then you can only make one cake. Chemical reactions work much the same way. The relative number of moles of each substance tells us the ratios and relationships necessary for that reaction to go. That information comes from a concept we just recently learned, which is balancing chemical equations. The coefficients in front of each substance in the reaction tells us the number of moles of each of those substances required for that reaction. So in this first example, you have 1 mole of N2, 3 moles H2, and 2 moles of Na3. Those relationships must be the same in order for this reaction to run. So you need 1 mole of N2 gas plus 3 moles of H2 gas to produce 2 moles of NH3 gas. This is referred to as the stoichiometric relationship or the molar ratio. Stoichiometric relationship or molar ratio. And this becomes, at this point, really the only new step for us because a lot of the work we've already done when we did our mole conversions in a prior chapter. So if you take a look here at our first example, how many moles of I2 are required to react with 0.429 mole of Al according to the following equation? So now I can, with a balanced chemical equation, I am now able to convert from moles of one substance to moles of a different substance. All the molar conversions that we did earlier were all of the same substance. We converted grams to moles or particles and so forth. Here I'm going to change substances, and I can do that if I have a balanced equation. So how would this first problem work? I would obviously take the number the problem gives me, 4.29 moles of aluminum, and I am going back to our conversion factors and factor label method. I want to get rid of moles of aluminum, and I want to convert to, they're asking me about I2, so I want to convert to I's a mole of iodine. If I have a balanced reaction here, then this is that value I'm referring to here. This is our molar ratio. So I use the coefficients in the balanced equation for those missing values. In the balanced equation, you can see I have 2 moles of aluminum and 3 moles of iodine. So I'll fill those values in my conversion factor, and I have successfully converted from moles of aluminum 2 moles of iodide. Quick math here, and I get 0.644 with the proper number of significant figures as my answer for moles of iodine. As I said a moment ago, the bulk of the work that we can do in this section is work we've already done. This molar ratio step or stoichiometric relationship is the only new step in the process. So if we think about what we already know so our only new step here is converting moles of one substance to moles of another substance. But if we think back to our roadmap that we did earlier regarding the mole, I know how to convert to and from the mole to grams or mass and to and from the mole to particles. If you remember here, we're going to use the molar mass of our substance here, and here we're going to use Avogadro's number to convert between moles and particles. So that means I can convert from grams or mass I should clarify, of substance A to mole of A, then use my molar ratio to convert to mole of B, and then I can convert back out to grams or mass of B. I could also convert from particles of A using Avogadro's number to A, and then back out to particles of B. We also recently talked about molarity. So since I know the conversion of molarity, I can, the conversion factor of molarity, I can convert from volume of solution A to moles. Here I would need the molarity. And then that means I can convert to volume of solution B, once again, if I had or could figure out the molarity of B. One other thing that we can do at this point, we've also seen and worked with density of a pure substance. So if I had volume of a pure substance A, I could convert to grams of that using the density. By pure substance, I'm referring to, an element. And then that means I could do the same thing back out on the other side here. Volume of pure substance B, and once again, I would do that with the density. So as you can see here, I have lots of possibilities of conversion problems and reaction stoichiometry that I can do here. But I want to reiterate, the only new step in this process is this conversion, this molar ratio, this reaction, the stoichiometric relationship here, which allows me with a balanced equation to use the coefficients to go from one substance to another substance. Let's take a look here at a practice problem, an example problem. As we have been doing all year, we always think about what is the problem asking for, what is the problem giving me. So in this case, this problem is asking for the mass of sodium hydroxide, NaOH. Okay, so I know that means grams of NaOH. And the number that I'm starting with, what's the problem giving me? The problem is giving me 16 grams of MgOH2. Okay, so once again, there's only one number in the problem here, so there's only one place I can start. So I'm going to take my 16 grams of MgOH2 and I'm going to start there. So in order to to do my molar ratio from mole of NaOH to mole of MgOH2, which is this second step right here, I must first obviously convert to moles. So I'm going to do that. I'm going to use the molar mass. I'm going to calculate the molar mass of MgOH2, plug that in there. So I've successfully converted to moles. So now you can see I'm going to go from moles in this second step, from moles of MgOH2. The 1 comes from the balanced equation here, the number in front of the balanced equation. Obviously, there's no number, so that's a 1. And I'm going to convert 2 moles of NaOH. And again, the coefficient in the balanced equation for NaOH is 2. So that's a 2-to-1 ratio. So that's my molar ratio, my stoichiometric relationship. Okay, if the problem was asking for moles, I would be done there. I would have successfully converted grams of MgOH2 to moles of NaOH. But since it's asking for mass of sodium hydroxide or grams, I'm going to use the conversion factor here, the molar mass of NaOH to get to our final answer of grams of NaOH. A couple quick notes here, and then we'll get into some practice problems on your own. When we did molar conversions in an earlier unit, it was okay for me to just use, when I put my units in here, moles and grams, because I was only talking about one substance. You can see here, as I label my numbers and my conversion factors, I need a little more information because of this second step here is going to be moles to moles. All right. And I don't want to get confused along the way. So I want to take a couple seconds and just make sure that I'm correctly labeling the unit, moles, grams, particles, along with the substance I'm talking about. I think that couple seconds can help to make sure you don't get lost along the way in the problem, because as you can see, there are a lot of possibilities here. So I would encourage you to label your numbers as you work through these problems with a little more detail. The other thing here is just to reiterate a point I made earlier. This problem could have asked for a bunch of different units at the end. It happened to start with grams and ask for grams, but if I had asked for particles of NaOH, then I would have used Avogadro's number here at the top instead of grams. So there's a lot of possibilities. So it's going to be really important for me when I read these problems to think about, what is the problem asking for, where am I starting, and then what is the problem, where am I going, and then what is the problem giving me, where am I starting, and then set up our factor label method here, our conversion to get from point A to point B. Okay, that's all for this 7.3 video. Now it's just a matter of practice, practice, practice. As I keep reiterating, lots of possibilities here. So just jump into some practice problems and make sure we get comfortable with this process.